Okay, so in A-level physics there are two laws related to magnetic fields that you need to be aware of. There's Faraday's law and there's Lenz's law, and both of which represent parts of an A-level where people tend to put the words down wrong, and because of that they start to lose marks. So let's go through it and make sure that we're aware of what both refer to. So Faraday's law, last time we looked at flux linkage, and that's the idea for a coil of wire, the flux linkage, that's one term, N phi, flux linkage is equal to the number of turns on a coil multiplied by the magnetic flux density multiplied by the area. Now, what we said last time is if we're going to increase the value of the EMF that's induced, we'd increase the number of turns on the coil. Now, the EMF that's induced across the ends of the coil of the wire is proportional to the rate of change of flux linkage. So if you do this quickly, okay, then what's going to happen is the value of the EMF is going to increase. This is Faraday's law, okay? So 2 marks referring to an induced EMF and referring to it's proportional to the rate of change of flux linkage. And simply, Faraday's law is written as EMF is proportional to the flux linkage or the change of flux linkage divided by the time. We'll talk about where the negative sign comes from in a minute, okay? But 2 marks, learn that Faraday's law definition. Okay, that equation is on the sheet that you're given in the exam, except that will be an equal sign. So if we plot flux linkage, which is measured in Weber turns, over time, which is measured in seconds, then we get a direct proportionality graph. Okay, in terms of Lenz's law is where that negative comes from. So let's say that we have got a solenoid, okay, so something that when there is current passing through, it will generate a magnetic field. Let's say we're looking down the end of the solenoid. If the current, okay, using the information that we've got from the power pack, if the current is flowing clockwise when you look down the end, okay, that is the south pole, okay? So if it's flowing clockwise around the current, that would be a south pole. Alternatively, if you're looking down the end and the current is flowing anti-clockwise, that would be a north pole, okay? So if the current is flowing south, okay, if the current is flowing clockwise, it's the south pole. Current is flowing anti-clockwise to north pole. Ways you can remember this, okay, there is an S in clockwise, so that is the south pole, or there is an N in anti-clockwise, and it's the only one with an N in it, so that is a north pole. Alternatively, you could put arrows on the end of the S to show that that is clockwise, and in terms of it's a bit false, but that's what you would do for north. Right, brilliant. So what we've got is something that can make something go infinitely fast, right? What we could do is we could get a north pole and we can have things going clockwise, so we've got south pole, we can chuck a magnet in, we can have lots of these lined up, and what will happen is it'll go at infinite speed. Not the case. Physics doesn't work that way, okay? So in terms of how physics works, we need to take into account the conservation of energy. So if we were to put a north pole into here, and this was a south, what would happen is that would turn into a generated north pole, okay, which would oppose the motion and slow it down, okay, and this is Lenz's law. So for conservation of energy purposes, we can't make infinite energy, I'm afraid, physicists. So the induced EMF, because we're going to induce the EMF by moving a magnet through here, is always in such a direction to oppose the change that caused it. So if we chuck a north pole into there, then a north pole will be generated across the end, okay, and vice versa. If we chuck a south pole into there, then a south pole will be generated across the end. Learn that definition, okay? The induced EMF is always in such a direction to oppose the change that caused it. It's only going to be an induced current if it's part of a complete circuit. So play it safe and talk about EMF. Okay? Right, in terms of practical uses of this, there's things called eddy currents and eddy current breaker, and we can look at that in a bit. Okay, but in terms of if we take a neodymium magnet, which is the small magnetic discs, and we were to put that into a copper pipe, Copper is not a magnetic material, but it's got low resistivity. Okay, so it's got a low resistivity value. You could do this with any metal, but I've chosen one with a low resistivity value. When we put that magnet down there, there is a change in magnetic field within the copper pipe. Okay, now because of that, that is going to induce an EMF, and because it's all connected, it's going to induce loops of current, okay, adjacent to the magnet as it moves down. Okay, because we've got current that's being induced, it'll also make its own magnetic field, because looking at the right-hand grip rule, we know how copper wire works, so that would make sense. Because of this induced current and then an induced magnetic field, the disc slows down as it falls through, and that's due to Lenz's law. And the reason why, the induced EMF is going to oppose the change that causes it. So as the magnet falls down, it's going to be repelled from below, and it's going to be attracted from above to oppose that change. Okay, look again, do a little bit of research, okay, familiarise yourself with these two terms. Thank you very much.